Here is a combined summary of the 2 pages. The escalating battles between attackers and defenders in cybersecurity necessitate testing and evaluating defense capabilities from the attacker's perspective. However, constructing full lifecycle cyberattacks and performing red team emulations requires significant time and domain knowledge from security experts. Existing cyberattack simulation frameworks face challenges such as limited technical coverage, inability to conduct full lifecycle attacks, and the need for manual infrastructure building. To address these limitations, we propose a AURORA, an automatic end-to-end cyberattack construction and emulation framework that leverages the capabilities of large language models, LLMs, in summarizing knowledge from existing attack intelligence and generating executable machine code based on human knowledge. AURORA can autonomously build multi-stage cyberattack plans based on cyber threat intelligence (CTI) reports, construct the emulation infrastructures, and execute the attack procedures. We developed an attack procedure knowledge graph to integrate knowledge about attack techniques throughout the full life cycle of advanced cyberattacks from various sources. We constructed and evaluated more than 20 full lifecycle cyberattacks based on existing CTI reports. Compared to previous attack simulation frameworks, AURORA can construct multi-step attacks and the infrastructures in several minutes without human intervention, incorporating a wider range, 40% more, of attack techniques into the constructed attacks in a more efficient way than professional red teams. The past year has seen a surge in the application of LLMs in cybersecurity, especially in cyberattacks. We identify the potential of using LLMs in a different way, which could make it even more powerful in attack construction and emulation. By combining LLMs with existing materials, we can effectively integrate information from varied sources, depict complex attack scenarios, and bridge human language and machine codes. However, employing LLMs in cyberattack construction involves complex challenges, including short-term memory limitations, correctness of LLM outputs, and ethical constraints. To overcome these challenges, AURORA harnesses LLMs to analyze CTI reports and existing attack libraries, expanding the attack technique library. It employs a knowledge graph to link attack procedures into a comprehensive full lifecycle attack and utilizes LLMs in conjunction with infrastructure as code (IAC) tools to automate infrastructure configuration. AURORA implements the chain of thought (COT) approach, segmenting tasks into multiple subtasks and designing a multi-agent system to mitigate short-term memory issues. By grounding prompts in specific technical details, AURORA ensures that LLM outputs are both accurate and ethically compliant, reducing the incidence of hallucinations and ethical breaches. Here is a combined summary of pages 3 and 4. This paper focuses on automated attack construction, which involves simulating attacks to assess defense capabilities. The process begins with a general plan outlining attacker profiles, techniques, and target scenarios, emphasizing thorough coverage of attack techniques. The TTP, tactics, techniques, and procedures, framework is used to categorize techniques based on their common objectives, providing insights into the types of information adversaries can access. Previous studies on attack automation have primarily concentrated on penetration testing, especially in stages like reconnaissance, vulnerability discovery, and exploitation. However, automated attack construction analyzes methods used in known attacks via logs and incident reports, helping to understand and anticipate TTPs to enhance threat mitigation and improve automated defense systems. The emergence of large language models, LLMs, has significantly advanced natural language processing, showcasing remarkable capabilities in generating coherent and contextually appropriate text from given prompts. LLMs have the potential to transform the cybersecurity landscape, particularly in planning and performing cyberattacks. Recent developments have demonstrated the use of LLMs in high-level task planning within penetration testing environments and vulnerability searches. However, building an end-to-end attack construction system faces several challenges. For instance, high-fidelity simulated attacks require analyzing messy human language reports and mapping sentences to standard attack patterns. Additionally, determining specific tools to use for each step and setting arguments meticulously are crucial for successfully executing the attack. Finally, building the infrastructure of the emulation environment requires meticulous operation by security personnel with domain knowledge. To address these challenges, the paper proposes an attack procedure knowledge graph, which serves as the basis of the attack construction. The graph is an acyclic directed graph where nodes represent procedures and edges denote relationships between them. Each node has multiple properties, including metadata, platforms, location, and executor. The graph is extensible, allowing new procedures to be added conveniently with the help of LLM. The paper also introduces the design of the knowledge graph, including nodes and edges, and demonstrates how to build it using LLM. The research discusses the development of an automated end-to-end cyberattack construction system, AURORA, which leverages the attack procedure knowledge graph to construct attack playbooks and configuration files. AURORA consists of four main components: report analyzer, emulation planner, infrastructure builder, and attack executor. The report analyzer extracts attack techniques from CTI reports, which are then used by the emulation planner to find suitable procedures for each technique. The infrastructure builder constructs the necessary environments, and the attack executor executes the attacks. The system's novelty lies in its ability to automate the construction of attack scenarios from various sources, including CTI reports, and its use of LLMs for analysis and extraction of technique lists. The paper highlights the importance of privilege management and the need for a Boolean variable to indicate whether a procedure requires higher privileges. It also emphasizes the significance of preconditions, arguments, and effects in procedure linking and execution. The summary concludes by describing the system's overall framework and its components in detail, showcasing its potential in constructing realistic attack scenarios for testing defense systems. The proposed system, AURORA, is a multi-source attack technique emulation framework that generates attack plans based on CTI reports. The system consists of several components, including the CTI report analyzer, emulation planner, infrastructure builder, and attack executor. The CTI report analyzer takes in CTI reports and breaks them down into small steps, mapping each step to the tactic, technique, and procedure (TTP) of the MITRE ATT and CK matrix. The emulation planner then searches for usable procedures for each technique, making necessary adjustments by adding supplementary procedures and omitting unmatched techniques to ensure the attack can be executed in real-world environments. The emulation planner takes the technique list as input and outputs the emulation plan, called the kill graph. The kill graph is a subgraph on the attack procedure knowledge graph containing the procedures selected for a specific emulated attack. The planner searches the procedure knowledge graph for available procedures for each technique, performs a graph searching algorithm on the procedure candidates, and considers each procedure's properties to form a complete kill graph. Procedures that are unable to be coordinated are discarded from the kill graph, and necessary procedures are added to the emulation plan, even if they are not mentioned in the CTI reports and the technique list. The graph searching algorithm is based on depth first search, DFS, and is shown in algorithm 1. For each technique in the technique list, the algorithm goes through the procedure candidates, checks if they are root procedures, and identifies their predecessors. The algorithm recursively adds the predecessors to the kill graph, ensuring that all preconditions are fulfilled. If a technique has no available procedures, the algorithm flags it as an unavailable technique. The generated kill graph shows the dependency relationships between different procedures, with arrows denoting the dependencies. The attack starts with root node procedures, which have no predecessor procedures required. The infrastructure builder component constructs the necessary infrastructure for the attack, using infrastructure as code, IAC, tools like Terraform and Vagrant. The system's limitations include the omission of critical steps in CTI reports, the unavailability of certain procedures in the attack arsenal, and the challenges of implementing social engineering attacks in an emulation environment. In this paper, the authors aim to leverage the capabilities of large language models, LLMs, to edit infrastructure as code, IAC, configuration files, and automate the infrastructure building process for attack simulations. The authors identify several challenges, including vague requirements for attack infrastructures, the need for accuracy in IAC code generation, and the requirement for detailed knowledge of specific IAC tools. They propose the infrastructure builder for AURORA, which addresses these challenges by incorporating existing human-written IAC code examples into the prompts for the LLM. The authors also introduce the attack executor component of AURORA, which utilizes the popular open-source attack emulation framework Kedar. This component translates the kill graph into ability, adversary, and source files defined in Kedar, and supports customized arguments for attack procedures in playbooks. Furthermore, the authors summarize the common principles of prompt engineering during their usage of LLM in constructing cyberattacks. These principles include using templates in prompts to standardize output formats, focusing on technique details in the prompt, and using examples to show the demand. The evaluation of AURORA's performance is presented, with a focus on different perspectives such as the completeness of constructed attacks, the coverage of tactics, techniques, and procedures, TTPs, in the constructed attacks, the effectiveness of the attack construction infrastructure, the ability of LLM to extract attack techniques from CTI reports, and the efficiency of AURORA in performing attack constructions and saving time and expertise. The results illustrate the effectiveness of AURORA in constructing full lifecycle attacks, improving the success rate of emulated attacks, and covering a wide range of TTPs. The research paper discusses the advancements in automated attack simulation tools, particularly AURORA, which leverages LLM for enhanced capabilities. It compares AURORA with other tools, such as attack range and CTID, highlighting improvements in success rates and TTP coverage. The paper also evaluates the effectiveness of the infrastructure builder, demonstrating AURORA's ability to create syntax-correct IAC files and deploy virtual machines successfully. Additionally, it examines the performance of the report analyzer, which extracts technique IDs and descriptions from attack reports with high precision and recall rates. The results show that AURORA outperforms other tools in several aspects, including TTP coverage, infrastructure deployment, and report analysis. The study concludes by discussing limitations and future work, emphasizing the importance of human input in security-related questions and the need for further improvements in LLM capabilities. The research paper proposes AURORA, an automated end-to-end attack construction and emulation system. It leverages large language models, LLMs, to process cyber threat intelligence, CTI, reports and generate attack plans. AURORA constructs the necessary infrastructure for attack emulations, offering a more efficient method for building diverse cyberattacks compared to existing solutions. The system's efficiency is demonstrated through user evaluations, showing that attacks can be constructed in less than 2 minutes. The paper also discusses limitations, such as the need for human intervention in certain stages and the requirement for specific software installation. Future work aims to address these constraints. The research contributes to the field by showcasing the potential of LLMs in automating attack construction and emulation, enhancing the efficiency of cyber threat intelligence analysis. The paper discusses the importance of semantic ranking for automated adversarial technique annotation in security text, as explored by Kumarasinghe et al., 52. This research aims to enhance cybersecurity by leveraging natural language processing techniques to identify and categorize threats from unstructured data. It highlights the potential benefits of integrating this approach with existing threat intelligence frameworks, such as STIX, 55, which is an OASIS standard for representing cyber threat information. Furthermore, the paper references Sun et al.'s survey on cyber threat intelligence mining for proactive cybersecurity defense, 53. This work emphasizes the need for advanced analytics and machine learning algorithms to extract valuable insights from large datasets, enabling more effective threat prediction and mitigation strategies. Additionally, the authors mention Bomjan et al.'s study on the effectiveness of sharing cyber threat intelligence, 54. This research raises questions about the actual benefits of information sharing in enhancing collective cybersecurity, suggesting that the impact may be limited due to various factors, including data quality and trust issues among participants. In terms of knowledge representation, the paper cites Sarhan and Spruitt's work on OpenCYKG, an open cyber threat intelligence knowledge graph, 56. This project aims to provide a structured and standardized way of representing cyber threat information, facilitating better data integration and analysis across different systems and organizations. Overall, the paper emphasizes the importance of developing and integrating advanced technologies, such as natural language processing, machine learning, and knowledge graphs, to improve cyber threat intelligence and enhance overall cybersecurity. It also underscores the need for further research on the challenges and limitations associated with sharing and utilizing cyber threat intelligence effectively.